It's a pleasure to have Dr. Brit Singh from John Deere joining us today. So for the EV webinar series, uh, welcome, Dr. Brit Singh. So to begin with, as you all know, electrification is becoming very big, and when we think about, mostly we look at electric cars and aircrafts and locomotives and so forth. But there's a very big and very important area that Dr. Brit Singh will be covering today. Those are off-road vehicles, construction vehicles, and several such vehicles which are also significantly moving towards electrification. I was reading somewhere that just by moving, like, not a full electric, but just say moving towards hybrid electric vehicles, some of the construction equipment can consume less, like probably 25 to 30% less fuel. So you can imagine how much of that impact will be there if all the vehicles are moving towards either hybridization as well as electrification. So with that, I would like to thank our sponsor, Evolve Houston, who has been really supportive for conducting this webinar series. And to learn more about the electric vehicle webinar series, and also look at the previous webinars, please visit the link which is shown on the screen. Um, I'm assuming there will be a lot of questions to Dr. Abridge Singh after the talk. So please use the chat function, using the live Q&A using in the chat function as shown here, and you can put the chat even through the talk, and we'll answer those once the talk is over. So again, welcome, Dr. Abridge Singh. It will be my honor to introduce him before his talk. So Dr. Brit Singh earned his BE from Madan Mohan Malviya Technical University in Gorakhpur, and an ME from Indian Institute of Technology Roorkee, and PhD from Indian Institute of Technology New Delhi, all in India, in electrical engineering. In 1996, Dr. Singh joined École des Technologies in Montreal, Canada, as a postdoctoral fellow. In 1999, he joined Concordia University as a research fellow. Later, in 2007, Dr. Singh joined the John Deere company as a staff engineer to lead and support silicon IGBT inverter development projects for the JD644K and JD944K hybrid loaders. In 2011, he joined Advanced Technology as senior staff engineer to lead John Deere's wide bandgap power electronics projects. In September 2020, Dr. Singh was named as the Region 4 Manager and External Relationships, with responsibilities to develop emerging technologies to support John Deere tech stack, production systems, product lifecycle, construction, and road building operations. Dr. Singh has published over 90 research articles, including papers in IEEE Transactions and IET journals. He has 28 approved US patents, one trade secret, and over a dozen pending patents. Dr. Singh received 4 IEEE Eta Kappa New Teaching Awards for outstanding instructions in electrical engineering. In John Deere, Dr. Singh has received 3 innovation and 1 collaboration awards for product and technology development projects. Dr. Singh is the winner of the 2020 IEEE Power Electronics Emerging Technology Award. In 2020, Dr. Singh was awarded the title of John Deere Fellow, which is a unique accomplishment in the leadership and position, and for significant contributions to power electronics engineering. In 2021, Dr. Singh was elevated to IEEE Fellow grade. He lives with his family in West Fargo, in North Dakota, USA. And again, congratulations once again, Dr. Brit Singh. It's a really great honor, especially coming from the industry. And with that, I would like to open the floor for your presentation. Thank you so much.
Yeah, thanks, Harish, and thanks everyone for having me here. Looking forward to my presentation and interactive. Stop me if you have any question. You can type in chat, and I'll pay attention to that, or I will answer them at the end. So I'll begin sharing my desktop, and please let me know when you see it. I'll put in
Yeah,
presentation mode.
yeah, we are able to see it.
Good. So I would be talking about wide bandgap powertrain system for heavy duty vehicle, and I'll talk a little bit about myself. Just like a conditioning of my mind, if you will. And then Deere and Company, just one slide. Then within Deere, there are various division. But ISG, which is called Intelligent Solution Group, the part of Deere I am deciding, is a technology branch. Actually, that's where we are developing a lot of unique technology for Deere and Company vehicle application, electrification programs. I'll talk about some of the electrification, mainly silicon IGBT based electrification. I was involved in from get go, ever since I joined Deere in 2007. And then WBG powertrain, silicon carbide, quite a bit detail about that. Then some vehicle testing, and then some experience, and then I'll summarize my presentation. So I have quite a bit slides, so don't pay attention to slide number because I hidden many of them. But anyway, these are relevant for this talk with time allowed, 30-40 minutes. So this slide talks about very, very unique thing. What that means is until 96, I was in India, northern India, and those who know at least India know very well that northern India gets very, very warm in summer month. In degree C, it gets as warm as 50 degrees C. And then I migrated to Montreal, as Harris mentioned in my introduction. It gets very, very cold in Montreal, about minus 40, minus 45 degrees C. And then I migrated to New Orleans. I was assistant professor in Tulane University, New Orleans, about 6-7 years. In New Orleans, as you know, it's a Gulf, so at the like Houston, it's basically gets very, very humid, hot, as warm as 40 degrees C. And then now I'm in Fargo, North Dakota, which gets very, very cold as a minus 65 degrees C. So now what you see here, a pattern emerging, right? Every time I move, I endure a delta C change. And that's exactly happens to power trans electronics. Whenever you are applying power, you get the, silicon material, silicon carbide material warms up. And when you withdraw the material, sorry, power, it get to the heat sink temperature. And that's very bad for powertrains, but without that, powertrain doesn't work. So temperature, that's what basically degrade the life of these systems. And if you design a good system, mainly packaging thermal management, then you could design a system that can have very long life, reliability, durability, and all that. So comprehending this effect is very, very important. And lucky me, in my case, I have seen it. So that's exactly, I feel like electronics is seeing similar thing. In Deere and Company, this is our basically the slogan called John Deere is a world leader in providing advanced products and services and is committed to the success of those linked to the land. Think about like a Deere has many, many business segments, and all of them are connected to some sort of like a working on touch on the ground, like a building, the construction, road building, right? Or maybe crop production, farming, all that, or turf care vehicle. So all that are related to land. That's why we are helping people those who are linked to the land. The division I am part of called as a intelligent solution group, and within that there are several branches brought together in 2022, sorry 2020, and that used to be called as a John Deere Electronic Solutions Fargo. Prior to that, it used to called as a Phoenix International. Phoenix is a bird actually who grew after his death, rose over the ISIS, right? So what I'm saying that the Phoenix International was acquired by Deere and Company, and now it is part of ISG organization. So there we make embedded controllers. So you name it, lot of vehicle controller on any vehicle, and Deere has many vehicle farm, and one vehicle is very different from the next one, has a very different form factor, different applications. So it's a very, very challenging how to manage that type of business. Then we have a Powertronics display user interface in this vehicle. What that means is as on a vehicle cab and Deere vehicle cab, there may be 4 or 5 displays, and the operator can take notice of what is going on. For example, when you are planting the seed on the ground during the seeding season, you can see how fast you are going, what camera is telling how you're dispensing the fertilizer and all this stuff, right? And same thing in harvesting time, right? In real time, you could determine the protein content in the grain, moisture content, and things like that. If you are going directly from the field to ethanol plant, let's say for corn, we would tell you, using advanced computing, we will tell you whether you are ready to go or not, things like that, right? So that's managed by display, business. And then wireless communication, all vehicles are connected with and they're so nice that during COVID situation we can diagnose any problem, miles and miles and miles away. And additionally, we push out the upgrades, so and then collect the field data, right? So using vehicle data, using satellite data, using weather station data, we can develop the model and tell that, let's say tractor is autonomous, right? Self-driving tractor, no operator there, and it need to go 20 miles from my location. I need to know what is situation at 20 miles away, right? So these gadgets are telling me that situation. And then sensing solutions, there are a lot of sensors in these vehicle, particularly as more and more automation is happening, more sensor would be coming in there. So this was one project that I started working when I joined Deere in 2007, called 944 hybrid loader. And architecture is, there are four electric machine, on one on each wheel. These are switch reluctance machine, SR machine. And the idea is that control system, electrification control system, has basically near zero speed tire spin and slicing. So we prevented that, because tire on this vehicle are very, very expensive. It could be $1 million vehicle and one tire is $10,000. So when you are working on a quarry mining, right, and you don't want to ruin those tires, right, and that was enabled by electrification. Also redundancy, like limp home in this vehicle, because if it fails, nobody there to tow you out and take it to repair location. So split drivetrain helps that. Additionally, this vehicle fleet has achieved industry leading reliability. What that means is, from my point of view, the hardware I designed for inverter have seen 50 plus million field hour and not a single failure. So I'm so proud of saying that. And particularly John Deere, quality, reliability, durability, and vehicle downtime is not option. Uptime is extremely desired. Other thing is that, if this vehicle goes down even for a 1 hour, it's a huge loss of productivity, because there would be additional 10 vehicle waiting in mining operation. So number I was told that if this vehicle goes down for 1 hour, it's a $3,000 loss. So we don't want to have that. So essentially, the SR machine, sorry, the generator, actually there are twin generator. These are PM generator on this vehicle. There are two generator connected on a common shaft, and the traction system is by SR machine. On the 644 loader, we have a, what you call, the consolidated transmission system, means one electric machine drive the transmission system, versus in the other machine, other loader, where each wheel has a dedicated electric machine. Here engine drive the generator at a constant speed, then it puts out electricity on the DC bus of power converter, and then you have 3-speed transmission system, right? And essentially what this is, Powertronics, right? So by delinking the what you call vehicle traction system from engine speed itself, has allowed what Harish was telling, just by hybridization, helps lowering the fuel cost or fuel consumption in these vehicle. And what we found, not only we could lower the size of engine, we have a 644 mechanical drive, like a all hydrostatic drive, versus the electrified version. By doing just traction electrification, we lower the engine size from 9-liter engine to 6.8-liter engine. And we are working on some further engine electrification technology can further lower the size of engine from 6.8 to 4.5-liter engine, right? So electrification, traction itself is helping fuel economy gain. And what is actually electrification enabling here is pretty much what it is doing. It is replacing the traditional torque converter. What that is basically, when you are working in a pile of dirt, you speed the engine, drop the engine speed, and then turn that energy into power into energy, right? Because when the engine at zero speed, power doesn't exist. We all know that, right? But energy exists. So you need a lot of torque at zero speed, and that's what happens in hydrostatic drive. But that's a very, very inefficient way of doing work, right? So by delinking engine speed or traction system from the engine, it has enabled quite a bit fuel economy gain in this. One question I often get to ask that, okay, these are hybrid vehicle. What is the size of battery in them? And answer is there is no battery. And the reason it is because 944 consumes roughly 9 gallon per hour fuel, right? A non-electrified version of 944 John Deere doesn't have, but we have a competition loader that is almost payload capacity 944 loader that consumes 24 gallon diesel per hour. So these are high energy consumption vehicle, and you don't have a battery, right? So the only thing you could do is replace inefficient system by efficient system, means electrified traction system, which is cyclic load, and that itself is a huge value prop, for customer. So there's no battery in both vehicle. Only the battery is in just to crank the engine. But here, this is architecture. So engine drive the generator, linked with the gearbox, at a constant speed, hardly be vary generator speed. And then inverter puts the electricity on DC bus here, and then transmits three-speed transmission system. And then when you are slowing down or driving down the hill, like a 45 grade 60 grade hill, like think about mine, right? Mine pit, you are going downwards. So at that time you start off the engine, and then you could generate the electricity, right? And you could have a hydraulic function. Or if you couldn't keep up the DC bus voltage beyond certain value, which is 750 volt, then you can burn that energy, regenerated energy, because at that time traction machine works like a generator machine, and so you need to protect DC bus voltage, right? DC bus component. So that's kind of pretty much like a protection. So now I'll switch over to wide bandgap technology, silicon carbide inverter, and this project was funded by Department of Energy through PowerAmerica. PowerAmerica Institute in NC State University, and they are doing very fantastic job. Particularly, adoption of WBG technology is happening because of the work a ecosystem that consists of many companies did for PowerAmerica and DOE. So I have a lot of slides, but I will talk only this because I want you to walk away with the impression, the mainly crux of what is the value prop of wide bandgap devices versus silicon carbide devices. So think about this. These are the characteristic, right? So silicon IGBT, and then super junction MOSFET, and then also the silicon carbide MOSFET. So if you look at the BI characteristic for a given current, voltage drop across silicon carbide MOSFET is much less than the silicon IGBT, and at the higher temperature also. So what that means is, particular traction system, car, vehicle, all that, usually full load is very rare. Mostly it is a partial load, and partial load efficiency is significantly higher. So we did efficiency mapping silicon IGBT versus silicon carbide inverter, and what we found that below 25 percent load, silicon IGBT inverter efficiency declines significantly, or at a low, at a high current and low speed also it declines significantly. But in silicon carbide, we always remain above 90%. In silicon IGBT inverter based drivetrain, efficiency goes down as less as 68%. So partial load efficiency are the extreme operating condition, corner condition operating efficiency is much better in case of silicon carbide versus silicon IGBT technology. So that's kind of advantage, and that's huge for particularly battery operated, where even each coulomb is very precious, right? So you want to use it effectively. So John Deere project in PowerAmerica. So Deere and Company is a founding member of PowerAmerica, which we had pretty good project experience working with Power America. So we had about $6 million funding. Now project is over and we tapped with additional Deere funding, and it was roughly $15 million type program for 5 years. So we were given very, very aggressive goal in 2000, 14 time frame, very, very extremely power dense. We were working until then 700-volt Powertronics began 1050-volt, and then super high efficiency, miniaturized power converter, low weight, and also the what you call that, as compared to conventional drivetrain, if fuel economy should be at least 25% higher. Another thing that we wanted go very, very high temperature powertrain, so we wanted to combine the engine cooling loop with the inverter cooling loop. In these vehicles, actually, there's one cooling loop for engine and one transmission system. Third is for engine and all that, and inverter. So idea was to eliminate the engine inverter cooling loop. So if you combine that inverter cooling system with the engine cooling, that's kind of like a vehicle level simplification. So that's what we did. Of course, this is advanced technology, emerging technology. There are a lot of risk being first in the field, right? And no experience, and how you solve those, issues. Because I'm not critical to the lab work that you guys do in university, but here it's like a going to work 10 hours continuously, right? A failure is not option. So you have to have design a system that works, right? Then supply chain issues are need to be addressed. But if you do innovation, there are competitive advantage to be had. So after successful execution of this project, we are working on production program. So you would see silicon carbide based, off-road vehicle, off-road vehicle coming out in market in some time soon. So we were given very aggressive goal metrics and all that. So 25 kilowatt per liter power density, we exceeded that goal. We gone 3 generation of inverter development. We are 43 kilowatt per liter. And in next slide, you see how the inverter look like as compared to silicon IGBT inverter. Efficiency, two-stage power conversion efficiency means power take in the input in the inverter and power output to traction machine. Two-stage power conversion efficiency should be 97% and higher. We prove out it is 98% and higher. And not only that, actually over the coolant, whether you run 25 degrees C coolant through the inverter or 115 degrees C coolant, and the region efficiency remains so high at full load, of course, because of the very good thermal management packaging we have designed for our inverter. Engine coolant, 115 degrees C coolant. So as I said, 3 generation. So Gen 1 inverter was proven out to be operating 105 degrees C coolant, and then Gen 2 was 115 degrees C coolant. And we found that Gen 2 inverter, despite 10 degree higher coolant running through the inverter, junction temperature was 20 degree lower as compared to Gen 1. And the reason is that because of better heat transfer coefficient, from junction to coolant, we design in this much better packaging and thermal management. And also, of course, we need to compete with silicon IGBT technology, and our numbers are indicating at system level we can compete with silicon IGBT technology. So this is progression of power density of John Deere inverter. So this is PD 550 inverter. This is actually in 644 loader. So a variant of this inverter is in 944 loader, different footprint looking, but the technology is same. And then we design what called PD 400 inverter. So PD stands for power drive, 400 stands for 400 ampere continuous current at a given switching frequency, 550 ampere current, 700 volt type inverter, 70 degree coolant. And then this is our Gen 1 inverter, silicon carbide by in housing. We gone from 700 volt to 1050, and we prove out 105 degrees C coolant operation. So ambient for electronics was roughly in the neighborhood of 120 degrees C, and here ambient was about 130 degrees C, something like that. So then Gen 2 was extremely power dense, and it was proven out on the vehicle, and in by 2018 time frame, and even I would say today, probably nobody has such a technology in the world. And even if they did have, they have not proven out fully on the vehicle. So proud to be associated with this project. So all these inverters are 400 kilowatt capable, provided you parallel output. So they have dual inverter, means they're two inverter, one drives the generator and drive the traction machine. And they are good for all sort of machine. They can drive a SR machine, induction machine, and PM machine. Then we done three generation, and this is very very small inverter. So modularity is very very important, because now inverter has gotten so small that it could be useful for many many vehicle. As I said earlier, John Deere has many many vehicle farm, and we may be having one vehicle model only 100 unit per year, right? So it's very difficult to design inverter for 100 vehicle per year market. But if you begin to use same inverter for many, many vehicle, all of a sudden you find that inverter usage per year may be as high as 10,000, 20,000, 30,000 inverter per year. And that's what economy of scale, plays in advantage to there. Increasing power density gives competitive advantage. What that means is, this is huge, right? This is 70 kilogram inverter. Weight wise, this is about 35, 37 kilogram. This is about 22 kilogram, and this is under 10. So you can imagine that doing same work, but how the power, specific power has gone up. It's a extremely power dense inverter. Decreasing bed size, form factor, is easier integration on the vehicle. For example, now this one is good enough that inverter motor can be placed together. You can eliminate the cable, connector, all that. And then of course, improve efficiency gives you system benefits, fuel economy and all that. So why heavy duty vehicles are so different? And the reason is that near zero speed operation requirement. So this is 644 loader. So engine is here. It drives through gearbox generator, and then there's a power converter here, then motor and brake resistance. But what if silicon carbide inverter can basically help us eliminate dedicated cooling system for inverter that will simplify the vehicle platform. So we did three generation of inverter development. So Gen 1 inverter. So when we got this funding in 2015, I had no knowledge whatsoever, just admit. Zero knowledge in silicon carbide, just only read couple of books and research paper. And now what to do with a lot of government money, right? So I thought, okay, let's go after the low hanging fruits, means, solve some of the problem, do some learning, and if it is risky, don't work on it, right? Maybe it's a good idea that if there's a possibility of failure, fail fast and walk away, rather pouring a lot of money, resources, and at the end of saying sorry, this wasn't a good thing, right? So I think a good engineering mindset would be that you want to give the risk, answer about risk very early on, right? And that's what we did in here. So we took our PD400 inverter, retrofitted capacitor with 1050 volt capacitor, also the power module, and then we did dv by dt filter, electric machine type, data collection to rewound 644 pm generator and traction machine to higher voltages. And within with no knowledge, within 10 months we were spinning electric machine. So that gave us enough confidence that yes, EMI, EMCs who are understood, dv by dt filter needed or not needed is understood. We know the capacitor, we know the suppliers, and also we are entertaining people developing devices for us. All that pathway became clear by doing this work. Then we took our what you call Gen 1 inverter, which was inverter in soon housing. We took Cree company power module, and so power density, our goal was 25 kilowatt per liter. We couldn't get that, but at least we did some additional improvement, additional learning curve. For example, understood importance of stray inductance is extremely important in wide bandgap Powertronics. And then we also did the characterization of inverter, making sure that it's good for 105 degrees C coolant. If inverter gets 105 degrees C coolant, nothing will happen. A vehicle will keep operating. Then Gen 2 inverter. So this is the unique power module. Some of you may have gone in conferences like ECCE or APEC or PowerAmerica. So a company called G Aviation System had developed this module for us. So I had quite a bit money in 2017 time frame, and about $500,000 money we put it to develop this power module. It is a three-phase power module. All the six devices are packaged together. We don't need the output bus bar, so the bus bar are integrated here. We eliminated voltage joint on the DC bus bar, all that, right? And some improvement how you gate drive interface with the power module, and then things like that. So then we developed this module, this inverter, and good thing is that both inverters are on the same side of the box, right? Earlier you have seen, PD400, PD550, and our Gen 1 inverter, they are sandwich, right? But here they are not, right? And this helps, rapid transfer of power from one drive to another drive, so the like stray inductance between generator and traction is much less here because enabled by this power module. And then we did characterization of electric machine and all that. And then due to miniaturization of power module, we realized power density goal 18 kilowatt per liter in our Gen 1 to 43 kilowatt per liter our Gen 2. Our goal was 25 kilowatt per liter, so we exceeded that goal. So we do lot of characterization. So we don't trust data sheet as it is. We basically take as a baseline, but we do characterization of power module over the temperature minus 45 degrees C, 0 degrees C, 25 and 105 degrees C testing at a power level, high power current. So like these are, like nearly 1000 ampere current switching, and this is like a load current like 250 ampere current switching, and want to see what is going on switches and all that. And we characterize all the switches, not only one. So in the three-phase inverter, like all six switches and all that. So that's what, and over the temperature. Sometime what happens, gate drive works nicely at 25 degrees C room temperature, but it doesn't work at a cold temperature and very hot temperature. So you want to make sure that the electronic circuit you design for these things work fantastically over the temperature. Then what we did was, so look at this comparison, right? And by the way, I have a lot of missing slides, but I think it's whatever you needed to know are here. So this is our comparison here, our Gen 0 inverter to Gen 1 to Gen 2, and look at this, how good it is to connect, like here, if I want to plug this cable, probably we are talking 2, 3, 4 minute time. Here it takes under a minute. So it is good for manufacturing, right? When you are put this vehicle inverter on vehicle. Additionally, maybe inverter and motor doesn't have any more cable. And indeed, we are working on program like this in production program, that we don't need any cable between inverter and motor, which is good because oftentimes these cables are much more expensive than the inverter itself, right? So you want to eliminate them. Shielding, connector are very expensive, and oftentimes connector is the failure actually because of the heating up there. So just get rid of them if possible. And this is basically the miniaturization due to wide band of devices is helping to do exactly that. So here, PD550 inverter, in 644 loader, 9 kilowatt per power liter power density, 70-degree coolant, and of course, inverter uses dedicated cooling system. This is one Gen 1 inverter, what tested on the vehicle, in 2017 time frame, and is 18 kilowatt per liter, requires much less space. So we needed to modify the cabinets. Inverter is here. So an operator climbs on the cab, he basically can put his step here. So there's enough safety built in, nothing will happen, even if there's 700-volt electronics here. We needed to do some modifications, which we did, and then we drove this inverter with the loader with silicon carbide inverter, and then hosted DOE to come and have a ride and drive event. So some lesson learned, over voltage issue with connector cable electric machine need to be understood very well. So for example here, right, power module wasn't optimized. So when we were switching, what you call 1000 ampere current at 1000 volt, we were seeing about 350 volt overshoot. And line to line voltage and dV by dt gets very high at motor end. So good design would be that very nicely packaged power module, and when you turn off the current, You don't return to lot of over voltage. Very good for inverter, but even extremely good for electric machine, reducing bearing current, shielding current, dB by dt related problem, all that are very well. So packaging is your answer actually, rather putting a snubber capacitor and things like that. And then of course bearing current IMC. So this module wasn't optimized, but this one was. When we were setting up about 1000 ampere, 800 ampere current at 1000 volt, we were just seeing only 10 volt overshoot. And the reason is that stray inductance in this one is in neighborhood of 0.25 nanohenry versus here about 0.45 nanohenry. So very well understood. So in silicon carbide, gallium nitride space, you need to pay attention to inductances, loop inductances, stray inductance, power loop inductance, all that. And that was good to learn through this project. Then another thing we do a lot of characterization, multi-machine, multi-inverter setup. So we have a 4 machine, 4 inverter setup to realize pretty much vehicle type condition. So first two inverter means there's one IGBT inverter, so half IGBT inverter, and one half of the silicon carbide inverter makes what you call like engine driven generator, and then other two halves are pretty much realizing the traction system. So what you see here, DC bus of silicon carbide inverter is not supported by any external source. So whatever dynamics you see in the vehicle, that can be simulated in the live environment. That's how I realized that the capacitor size of the inverter can go down significantly. So you saw those inverter earlier, right? PD550 to our Gen 2 inverter. We have reduced capacitor from 13, pay attention to this number, 13,000 microfarad to under 440 microfarad. Actually, our simulation was indicating 280 microfarad, but we did not find any. So just we produce inverter our Gen 2 with 440. So how you see that not only by simulation, like simulation, hardware in loop simulation followed by experimentation in lab, how you know that this is good enough, and that is done by experimentation. You do day night calculation, but unless you feel by experimentation, um, you don't feel that confident. So that visual diagram that you saw in previous slide is actually look like this in the live environment. So this is our silicon carbide inverter, Gen 2 inverter, and then this is our silicon IGBT PD400 inverter. This drives these two machines here, and then this one drives these two machines rewound for higher voltage, 690 volt line to line. So 4 machine, 4 inverter setup allowed us to simulate 644 condition in the lab, like operator driving the loader. And then these loaders are day long, going high power, low power, high power, low power. So we want to make sure whether when we reduce the capacitor from 13,000 microfarad in PD550, which is production 644 loader, versus 440, and whether DC bus will remain stable or not, right? And then we found yes, indeed, and that was based on many, many things: packaging, thermal management, cooling of the capacitor, and control, right? Feed forward control and things like that. And indeed, we found that abrupt change of power from 30 kilowatt to 150 kilowatt DC bus had a sag, but it recovers quickly, fast. And same thing when you throw away the load from 150 kilowatt, 30 kilowatt, inverter DC bus remains stable. So that's how we tested power shift characteristic of loader. And then this is YouTube link. I'm not going to play the low, in interest of time. Maybe let's play this, and because I have few minutes, I can show it. So the loader was driven by silicon carbide inverter. I will bring in this screen. Yeah, so this is being driven by silicon carbide inverter, cooled with the engine coolant. So I would like you to pay attention to tire slippage after some point, and then I want to explain one very unique benefit of electrification. So operator does whole day long forward, backward, and which is very bad for these vehicles. So here, when it's pushing, this tire slips, right? 944 loader is not desired to do such a thing, because otherwise you will real quick ruin the tire, so that's why we don't want to do that. So let's see, keep going. So yeah, our aspiration was to go 115 degrees C coolant. And what we found when we sweep the coolant, at 150 kilowatt power, 25 to 115 degrees C coolant, junction remain below, 175, 145 degrees C, and junction remain 30 degree above the coolant, no matter what coolant temperature you put in. And the reason is that because we have very good heat transfer, from junction to the coolant. Also, we eliminated a lot of thermal layer by doing a lot of packaging and all that advantage. But what we found, gate drive temperature was rising above 130 degree ambient, and there were a lot of gate drive, silicon chips in the gate drive that were 150 degree rated type devices. So then we did some thermal treatment, means blocking the heat from the surface of our module going up in the air in the within the box. And once we did that, then after that, no matter how hours and hours and hours long we ran continuous 150 kilowatt power with 115 degrees C coolant flowing through the inverter, and no problem. Now you may ask, why 115 degrees C coolant? The reason is that because once a while in 644 loader, engine coolant go 113 degrees. So if we want to run engine coolant through the inverter, better inverter should be designed to run at a higher temperature. That's why 115 degrees C coolant qualification was must. So in summary, I would say early adopter, the silicon carbide powertrains is real, and in past 6 7 years, massive change has happened, and across the board, like a supply chain, material, devices, packaging, thermal management, applications, all that happened. And we I believe that based on the learning we made in Deere and Company, by 2025, silicon covered MOSFET technology very successful will compete, and maybe it will compete out by 2030 to silicon IGBT. Maybe it could happen that mainstream device for power particular traction, vehicle traction, could be silicon covered MOSFET as gallium nitride, FET versus the IGBT. And then we have a lot of experience from vehicle and benchtop testing and all that. Cost reduction, of course, happens. It will never happen that the silicon carbide MOSFET at device level or die level will ever compete with the silicon IGBT, but system level it will compete, right? So you need to have take the system approach, eliminate lot of cost that are with the silicon IGBT. You can, like for your capacitor, right? 13,000 microfarad to under 440 microfarad. That is huge, right? We reduce capacitor, by the way, cost by 10 times and size by 5 times. It's come PD 400, and so many other things. Another thing, innovation has to happen. Like I called it innovation by C solution. I kept capturing this C, right? Capacitor, right? We reduce capacitor. We coolant, we gone high temperature coolant from 70 to 115. Connector is very well simplified here versus here. Case, overall size has shrunk. In the decarbonized, carbon market and all that, dematerialization is very good. You use less copper, less aluminum, less plastic, which is very, very good for sustainability, environmental sustainability. Control, we could put fast control loop on DC bus. We can do dual rate control, higher bandwidth of the inverter control system. That makes dynamics much better. That came because of the high switching frequency of the devices. Also, the coreless current sensor. In current sensor, Hall effect based current sensor, core based sensor, the core heats because of couple of things. One, fundamental magnitude, frequency of fundamental, and switching frequency. Once you want to go very high switching frequency, better you want to get it up that core. So that's exactly we did here, and also miniaturize the. So we reduced the core current sensor cost by 2.5 times, size by maybe 2 3 times. The copper, overall copper content be reduced, right? And the cost, of course. So those were kind of innovation we did. Okay, so I would like to thank Department of Energy for funding this project through Power America, and the packaging, thermal management, thermomechanical stress characterization, all that. Because when 115 degrees C coolant is flowing through the that power module that you saw, there's a lot of thermomechanical stresses and all that. And yeah, so that was basically done. Computational analysis was done by enrolled scientists, and then of course Deere management, my team in John Deere, and to letting me work and providing that $8 million cost share. So another thing I want to share a good news that recently I was given award letter from DOE that I would be again leading one more project in tune up $2.75 million funding, and where what we would be doing with Deere match, it would be $4 million project over 3 years, and we would be doing electrification of articulate dump truck there. And the overall societal impact is basically innovative diesel electric hybrid powertrain that we would develop. We would have a battery also integrated with the inverter, and overall carbon footprint reduction will happen, multi-metric million metric ton greenhouse gas reduction. That's kind of our objective, making green technology for our customer. With this, I will be happy to answer any question you may have, and this is my email address. Please write me if you have any question on this presentation, or you want to hear my thought on anything else. I mentor a lot of people in university, so I would be happy to give my time to you. Thanks for having me, and I would be happy to answer any question you have.
Thank you very much, Dr. Bridge Singh, for an exciting presentation. So definitely, that's something which we learned a lot. And so I do see two questions, but I think you have more or less answered both of them. The first question was, what drives the need for 105 degree C coolant for power electronics? So you mentioned that that's basically it's coming from the thermal management system, right? So do you want to add something on top of that, or?
Uh, yeah, I'm mainly taking the advantage of. So our aspiration is to get rid of, dedicated cooling system. So like 644 loader, you saw there, right? So there are multiple cooling loop there. One is for engine transmission system, and then also the inverter. So what if we could get rid of inverter cooling loop and run the engine coolant through the inverter? And if we did that, because inverter is at 70 degree C coolant, inverter
Yep.
coolant will never go more than 70 degree.
Mhm.
So engine goes 113. So that's the reason we
Okay,
just qualified.
sounds good. Yeah. And the other question is, when do you expect silicon carbide inverters to be able to achieve price parity with silicon inverters? And what are all the biggest challenges that you see in the scaling?
So at system level, I would say system level means overall drivetrain has already achieved the parity. At the device level, it will never happen. At the inverter level, also probably may not happen. But you have to add the value prop. So, like for example, let's say I use 10 kilogram aluminum in the inverter box, right? Silicon IGBT inverter, and all of a sudden I need only 2 kilogram because the power density is so high. I get it off 8 kilogram aluminum in the silicon carbide based inverter. Then you begin to calculate 8 kilogram aluminum saving and carbon footprint that has produced. So if you begin to, because now industries are going to put their sustainability goal out there is scope 3, which is basically entire life cycle analysis of their product, right from bell to wheel type, carbon footprint calculation. So I believe the value prop that this technology will bring from material side and dematerialization of the materials, is huge, right? So if you look at from that, like you have to do the value prop, and system level approach, and if you did that, then yes, indeed, it will begin to compete pretty soon. But device level, no. Because die is just very small, right? There's no material there, much other than semiconductor.
questions, please feel free to post it. So I do have a couple of questions. One is, so you mentioned about 700 volt DC bus, as also, like, I believe the 1050 was the rated rating of the capacitor. Is that correct? 1050 and 1100.
Yeah, so that's a DC bus voltage, Haris.
Right.
The capacitor were about 1210 volt rated
Okay.
at 85 degrees C hot spot. So we made sure that the capacitor voltage never ever goes more than 1175,
Okay.
and also internal hot spot temperature in the capacitor never goes more than 85 degrees C.
Okay.
Even if you have a 115 degrees C coolant, even if you have 130-degree ambient
Okay.
in the power stage, but the capacitor never ever sees more than 85 degrees C internal hot
Okay.
spot. So
Okay. So the question is, like, I know, like, regular cars, they are. I mean, I briefly worked for Ford, and that time, it was almost 300 within 350 volts DC bus, and then like, now we see a much more wider range, and people are talking about 750 volts, 800 volts. So on in off-road vehicles, like the dump truck or construction vehicles, what do you think will be a sweet spot for the DC bus? Like, have you already reached this sweet spot, or do you think there's some more exploration needed there?
yeah, so basically the DC bus voltage in electric car would be driven by battery technology.
Right.
So it seems like 800 volt is basically convergence there. For off-road vehicle, we aspire to use whatever on-road vehicles are battery technology, same thing we would use off-road. And if their volt is 800 volt and we directly put battery across the inverter, then that's it. That's one. Another thing is that rest of the component, like finding a connector at higher voltage is not very easy. It's
Yep.
a huge challenge. Or even electric machine, then insulation coordination, all that. So all that, I think this voltage that we talk about, multi-level inverter and all this stuff, is good for academic research, multi-level inverter, and all this stuff. But industry will only adopt if there are rest of the component fall in place. And one of the challenge I see electric machine, voltages and all that. So in Deere, since we don't have a million vehicle market per year, so it would be extremely difficult for us to customize a machine and it get the cost target. So we want to use whatever available in the on-road, and that
Okay.
seems like indicating 700 volt to 800 volt.
Okay. Sounds good. And one more question, like, you were talking about the machines. I believe most of the figures that you showed, they were using permanent magnet machines, if I'm correct, right?
Yeah,
Uh,
yeah. We in 644 both machines, traction and generator are permanent magnet. In
okay.
the 944 machine are wheel machines are SR machine.
Okay.
We got the constant speed torque ratio and all that,
Okay.
that range, and also the but generator is a PM, and at that time get the way because that has a by the way the 944 machine ground torque is 1 million Newton meter,
Hmm.
so we have to produce that torque, right, to push
Yeah.
push the thing in the concrete.
Right.
It's very hard to find that time PM machine wasn't there, right? So we
Yeah.
use SR machine.
So you're already using SR machine. So that was my follow-up question. Like, are you using somewhere? So that's good to know.
Yeah, 944 loader uses SR machine. Yes.
Okay. So, and like, probably this will be my final question. What are some of the differences that you see? Like, you said you want to use, like, probably a similar power drivetrain just to save costs, like, on multiple products, right? So what are will be some of the challenges in different applications? Like, you have loader that you explained, and then I think congratulations on your new grant, which is on the dump truck, correct?
Yeah.
So what do you
Dump truck,
see
yeah.
the differences in the challenges will be, and how do you adapt?
Yeah, actually, mainly software. So, like a dump truck has a lot of idling time.
Yeah.
So, like a 78% idling time. So, the idea to put battery there was to get rid of idling time means when vehicle is doing nothing, engine is cranking, can you shut off the engine? But still, you need power for some things, right? So, for there's a battery. So, that would be one, right? How you successfully interface the battery. Another thing is that software differences, like these inverter, like 6 switch inverter, three standard 2 level inverter. Now you can repurpose that to drive induction machine, SR machine, if you want, or PM. So I think software can capture a lot of differences. Another thing, from one vehicle to another vehicle, mission profile would be very, very different. Like for example, tractor versus loader. Loader is highly cyclic load, like comes goes type load. In tractor, you continuously driving at a very, very high peak power, right? When you are driving, let's say you're driving a planter, right? It's always very, very high load. So you have to design it for maximum rated load, but then maybe less usage, right? Tractor maybe use only maybe 1,000 hour per year, right? Whereas a loader maybe whole year long and things like that. So mission profile is another difference. Then the operating conditions. These vehicles are used world over. Canada, upper region, frozen region versus in Arizona. So you need to understand those differences, all that in Powertronics. So as much modularity we try to design, maybe there would be some differences, right? But then we took a histogram that what are the maximum, what is the thing that can be used most of the time, and then go from there.
Okay. Yeah. Thank you so much. I think we are just on time. So we would really like to thank Dr. Britsing again for this exciting presentation and patiently answering all the questions. And as he mentioned, if you want to reach out, like please feel free to email him. And we also want to thank our sponsor Evolve Houston. So it has been a great presentation, and hope you all enjoy your weekend. Thank you.
Thanks for having me. You all have a great weekend. Bye.
Thank you so much.